Now, fuel grade aluminum, when we make aluminum today for, this aluminum on my iPhone, right? This is aluminum here.
For this
Yeah,
tea can that I'm drinking out of, right? Like,
exactly. This has to be, when you smelt this, 99.7% pure. Okay, those impurities are really, really important. I need 88% pure.
yeah,
Okay,
that's great.
right? So
That's
now
a great threshold to have, right? Like that's way easier than 99.
it's way easier. It's
I
way
mean, it's kind of
easier.
like school, right? It's way easier to get an 88% on a test than a 99.
It is way easier to get an 88%.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country
Of course, the world cannot meet it without America.
that is willing
We're
to
going to need you, the next generation, to finish the
overhaul
job.
nuclear
We
regulation
need scientists to design new
and
fuels.
focus on net public
We need
benefit
engineers to invent new technologies. We need
over absurd levels of radiation protection,
entrepreneurs to sell those technologies.
then we will march towards this.
We need workers to operate assembly lines that hum with high-tech,
where we
zero-carbon
have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Okay, welcome to another episode of the Fire to Fission podcast, where we talk about energy dense fuels and how they can better human lives. Today I'm joined by Rob Alexander, the CEO of AlumaPower Corporation. So, Rob, how you doing, man?
I'm fantastic, Mark. Good morning to you.
Good morning. Yeah. Really, really excited about this conversation. We've got kind of a different technology, but claims for more energy dense batteries, even more energy dense than lithium ion, which is very fitting for the show. So, Rob, for the audience's perspective, I guess, do you want to give a quick 30 to 60 second overview of kind of AlumaPower and what it is that you guys are chasing?
Yeah, sure. So essentially what we've done is we've reinvented the aluminum air battery. And an aluminum air battery in some ways is a misnomer because when you extract energy from the aluminum, it's kind of a one-way transaction. It's not like a rechargeable battery like lithium ion. It's more akin to a diesel generator where you put diesel in and you get electrical energy out. And I'll get into that and discuss exactly what we did to change it. But essentially what it now means is we've got this generator. We call it a galvanic generator that, where you take fuel in the form of a fuel disk, and some people will see video. This is a fuel disk. This would go into our device, and it would produce clean electricity and heat if you can use it. And that's really the story. And so it becomes a wonderful new way to transport energy, clean energy, and then extract it wherever you need it. And that's what we're doing.
That's awesome, man. Good, good for you. Very exciting. I'm stoked to dive into kind of the tech and technical details. As you said before we started recording, you could tell from my public persona that I'm a nerd, and so I'm stoked to talk about it more. But first, I want to learn about you, Rob. What's your background? Where are you from? How'd you get your start in the energy space?
There you go. Well, I'm 61 years old, so man, we could talk forever, but I won't.
You don't look 61. The peg's younger.
No, I'm 61. I'm fully 61. I guess, yeah, I was thinking about how to answer the question, and, it's, I thought I might start with a story, actually, because it got recounted to me by my grandmother not that long ago. 7 years old, if you could imagine being 7, and I love to build forts, and so I kind of, I was at this stage, I built one that was on the ground. I thought, okay, what's the next step? Hey, I'm going to try for a tree fort. And so my parents were away. My grandmother was taking care of me, and I think I was in grade 2, and Canadian and in Canada, grade 2, you haven't really studied a lot of physics and leverage and things like that. But I'm like, okay, I'm going to build this thing. We lived in a subdivision, and there was lots of wood around. So I had this nice piece of plywood, and I'm thinking, okay, I'm going to build my fort up there in that tree. And so I'm like, okay, how am I going to get that wood up there? I'm all alone. And I'm like, oh, I found this rope. I'll tie the rope to the wood. let me see, one on the plywood. I'll take the other end. I'll climb up the tree, and I'll try and lift this thing up into the tree. Tried that, and I'm like, oh, I'm gonna fall off. That's not too smart. Got to be smarter than that. So then I had this brilliant idea, Mark, and I said, okay, what if I take that rope and I tie it around my waist, and then there's this nice branch. I'll just jump off the branch, right, and try and I've done it. It's about 8-10 feet up in the air. I've kind of jumped from that high before. I'm just going to jump off and land on the ground, and then it'll pull the piece of plywood up into the tree. And that's what I did. I jumped off, but I kind of failed to kind of think through on a whole bunch of dimensions. Like what was I going to do when it got up there? But the biggest issue was I didn't really figure out which one was heavier, the piece of wood or me. And so as I flying down there trying to land it with my feet, all of a sudden I get whipped up, and now I'm dangling over top of the ground. I can't touch the ground, and I've basically the board didn't move. So that kind of, and that's where I started. I've always been curious. I like to build things. I'm impatient, somewhat stupid, and it was scary. And the reason I bring it up is because my grandmother had told me this story, and I'd completely forgotten it. But I thought, man, that kind of summarizes a lot of what I'm like. So there I was dangling. It was bad. I didn't know my knots, so I'd actually made a slip knot around my gut, and so that thing was really, really tight, and I was starting to panic a bit. And so I did what any 7-year-old does. I started screaming bloody murder, and my grandmother thankfully came out and rescued me. So that's kind of where I think I was just built that way. I mean, I think, that's a young age. I've got my grandson upstairs, and he's a little bit like that, just curious. I would say the other big influence for me was really my father. So he's an entrepreneur and also an engineer, chemical engineer. Didn't like chemical engineering and then went into business. And he had a huge impact on me. I did pretty well in school, so ended up wanting to follow a little bit in his footsteps. Went into engineering, got into Princeton down in New Jersey, took electrical engineering, computer science. But before I'd gotten there, I'd actually worked a lot in the family company. And I really got a feel for, how they work and how bigger. It wasn't a huge organization, maybe 100, 150 people. But, family company, always borrowed, money from the bank, covenants. There's a lot of covenant pressure. So, end of the month, we had to make our covenants, call the kids in, and I'd be working my forklift or doing whatever on the weekends, to ship products. So you really learn when you're in a family company, you learn and get exposed to businesses. And that had a big influence. So went to Princeton undergrad. One of the things my father kind of failed on in a few different ways, he said, is, Rob, if you're going to go into business, you got to understand finance. You got to understand how to value businesses. He kind of messed up a bit. And so I, kept coming out of Princeton. I'm an engineer. The obvious thing was do something related to your degree. Instead, I just knocked on every door on Wall Street possible. I think it was 21 of them. The 21st one let me in, which was Kidder Peabody. So I worked on Wall Street as an analyst, which was fantastic. Took a company public, did some M&A work. So that gave me an exposure just to the finance side. And then 87 hit, which was this big crash. I just gotten my company out public 3 days before the crash. And so I was traveling around the world.
Friday or Black Monday or?
Yeah, it was Black Monday,
Yeah.
Exactly.
Yeah.
Yeah, we got out on that. We were the last IPO before that crash. Company was called HMSS. It was a home medical care company.
Rob, I
First of its
can
kind.
tell you already, you like learning lessons the hard way, right? From
Yeah, I'm stupid. Yeah,
how do I learn about physics? Well, test with my body as a 7-year-old, right? Build this human pulley system. How do I learn about finance? Take the IPO, right?
Well,
before
it's
the market crashes.
Mark, it's smart people. You've heard this quote. I forget who said it. Smart people learn from other people's mistakes. I'm not that smart. I tend to make it once. I do try not to make the same mistake twice. But yes, that is very much, it is a little bit of the mentality. So anyways, then how did the whole tech thing happen? I got in, I was traveling around the world after they gave us some money to go away in that 87 crash, and I was traveling with my wife. MIT was kicking off this new program called Leaders for Manufacturing. And it's kind of interesting in the context of what's going on in the States today. Back in the late 80s, a bunch of the companies in United States, like it was Ford and General Motors and Alcoa and Hewlett-Packard, that what they were seeing was that Japanese were really dominating industries. And so they said, we got to get manufacturing back in the United States. And so they created this program at MIT. And the whole design was put the business degree together with the engineering schools and try and break down the barriers between not just the business, Sloan, and the engineering, but also between the disciplines in the engineering group. Okay, and it was started by a guy named Les Thoreau and a bunch of others. So they said, hey, Rob, we saw you, would you be interested in coming to this? And so I did, and I got a scholarship to go there. Had a huge influence. Okay, now I can use my tech, use business, how am I going to put these things together, and really focus on manufacturing and operations, which I do think is a really important piece of how you create value. So, long-winded answer, Mark, to your question, that's how I ended up kind of with the interests in technology, manufacturing, and business, and kind of putting it all together.
That's awesome. I think that's one of the best answers I've ever heard, especially with the anecdote as a 7-year-old. Like, what a crude awakening into like physics 101. That's fun. Okay, well, Rob, you as you said, you're 61. You've had a career since then. Why don't you just tell us about some of the stories that come to mind from your career that kind of led you up to the company that you're at now? Up to AlumaPower.
Yeah, so if I kind of fast forward about basically what happened, as I mentioned, my father was an entrepreneur. I left MIT, I went and worked at McKinsey, which that program was mad at me for doing it, but I was doing strategy operations for about 3 years, living on a plane. My daughter was born, and I was, this isn't going to work for me. And my wife, I just can't. I gotta spend more time with Chelsea. And so at the same time, my father had built his business, and he was like, son, I'm going to sell my business. And I said, wait, I probably am overconfident. I thought I was pretty good at finance. I said, Dad, before you sell it, let me take a look. I might buy it from you. And so I left McKinsey, came work with him, and ultimately did a big leverage buyout at the age of 32 and borrowed a lot of money. I think it was $68 million, and bought this business from him, which in hindsight was also stupid. I really leveraged. I didn't really listen in my finance classes, and I leveraged a company that shouldn't have been leveraged like that. But it also is kind of the way you learn, and you have to survive. So the company it had successes and failures. We grew it from about 10 million to 120 million. And it was an automotive supply company. We had a trailer hitch company, and we had another one that sold to the car companies. And I learned everything there. I made big mistakes, just like jumping off the tree. Learned from it, and eventually I had a fair bit of success with that company. And then about 2008, everybody kind of knows about what happened there. Automotive, I had both General Motors and Chrysler call me within 72 hours, say, hey, we're going bankrupt. We're not going to pay you. I think they owed me like $40 million. Sorry. Big deal, for me. Had to restructure the business and do all that stuff. That wasn't fun. But about that same time, two guys came to me, a guy named Hank Van den Ende, this big, gregarious Dutchman, sales kind of oriented guy, and he's with his good friend, Jeff Sheeran. And Jeff is this incredible inventor and the CTO of AlumaPower. And just a fantastic lateral thinker. Like I'm a decent engineer. Jeff is a brilliant inventor, creative thinker, and all the creative genius is in Jeff, not me. And Hank had kind of taken it upon himself and said, how do I help Jeff? And so they approached me, and they'd heard about me in business and these different things I'd done. And they said, would you help us take these ideas from Jeff's brain and turn them into commercial successes? And we talked about values. What are we trying to do at this stage? We want to take this tech, do some good for humanity, the world, especially those most in need. And that's kind of been our mantra for 15 years. And so we've done a lot of things together. We did a a business where we injected hydrogen into a diesel engine to improve the fuel economy. That's a company called Dynacert now. But then about, I think it was 2017, Jeff called me up and said, Rob, I think I've reinvented the aluminum air battery. And I'm like, Jeff, what the heck's an aluminum air battery? Never heard of it. So he talked me through it, and as we kind of built the first prototypes, I funded the first patent. That's where it became clear. Wow, Jeff, I think you might have a big one this time. That was the beginning of it, and that's where we are today, building that same tech that he invented back in 2017.
That's awesome. Well, I don't want to waste any more time talking about. I mean, I'm sure we can come back to other stories if we have more time. But I want to learn about this air battery. So. To tell us about it. What in 2017? I mean, that's relatively recently, right? On your LinkedIn it says 2020 for joining this group. Let's start with the tech. What is the tech?
So let me explain aluminum air. So when you make aluminum, you inject a whole bunch of energy into it. Most of the aluminum in North America is made in Quebec, the province of Quebec in Canada, and it's beside a hydro dam, and what you're doing is it's an electrolysis process. And so I'll go a little deep into the tech, and essentially you got two plates. You're injecting all that energy in there, and you attract the Al, the aluminum, to one side, and that's our aluminum that we use. And what we're really doing is we're getting all that energy back. Okay, but we're doing it at the end of the cycle for that aluminum. It's been recycled maybe 20, 30, 40 times, but eventually it becomes too dirty to be used cost effectively to be recycled again. And that's when we pick it up. So we're kind of like an end of life, a waste to fuel option. Now the way aluminum air works is you take a plate of aluminum. It's pretty simple. You're just reversing the process. Aluminum on one side. On the other side you have an air breathing cathode. So you've got oxygen coming in the other side, and that cathode is kind of like our lung. Okay, and so on the one hand you got the cathode, the other side the aluminum is the anode, and in between is an electrolyte. We use sodium hydroxide, which is Li. Okay, and all you're doing is you're corroding the aluminum. Okay, the oxygen is coming in. You got the actual chemical equation is you're going to AlOH3, and in that process you're releasing 3 electrons, which we're taking off of the cathode and anode side of it. It's that simple is really what's going on. Now, what wasn't simple though is those were invented in the 60s back in the United States and Canada, and the issue was they were invented by electrochemists and chemists, and everybody thought batteries stationary, so plate of aluminum, air breathing cathode. Jeff's not an electrochemist. Jeff is a man of, he's actually an industrial designer, self-taught really. And so he's like, wait a minute, I understand mechanical, how do I approach this? The fundamental problem and the reason you haven't heard about aluminum air, there's a few problems, but one of them is that when you wanted to stop the reaction, you would drop the electrolyte, it would passivate the surface. And if you put the electrolyte back in, it wouldn't work again. So the military uses aluminum air for like one-strike things, like torpedoes or drone strikes. You add the electrolyte, it works. It's very high, high energy density, but you couldn't start it again. It doesn't matter with a torpedo; it kind of goes one way, right? So that's why you never saw them scale. So Jeff goes, well, wait a minute, how do I stop that passivation? And he was inspired he's from Scotland, inspired by some boats that were getting rid of water on their windshields with a rotating thing. He said, what if I rotate it? What if I rotate this disc? What if when I take the electrolyte down, I actually spin this really, really fast, cause all the electrolyte to spin off and dry quickly before the passivation layer gets created? And he tried it. It was like, ooh, it works. Now I can stop and start this thing. Okay? And that was kind of the key breakthrough. The other thing, though, and so much more came from it, by making this into a disc, he also made it simple to load and, sorry, this background's not very good. I almost wonder if I should get rid of it. Load and unload. So now it's kind of like going into a toaster, or a CD drive. Simple to refuel. Instead, before they had to kind of disassemble that whole battery. And, it was really a battery swapping type of thing. But the big breakthrough, and one that was completely unplanned, was when you used the aluminum in this disc format, instead of having to use pure aluminum, which most aluminum air batteries had to use, you could use dirty aluminum. And the reason that's important is that there's a parasitic reaction that creates hydrogen. And that's why everybody would go use pure aluminum, which of course drove the costs through the roof. It made it basically uneconomic for most commercial purposes. But we didn't have any pure aluminum, so we started with dirty aluminum, and we're like, oh, shoot, we're getting numbers that you're not supposed to be able to get with aluminum air, right? With dirty aluminum, and all of a sudden we're like, oh boy, this is starting to look really good, because now the cost of our feedstock is reasonable. It's waste. And so now we actually have an energy carrier that can be cost effective, clean, safe. This fuel, it doesn't explode. There's no thermal runaway issues, none of those safety issues. It's known technology. Prevalent. Aluminum's the most prevalent metal in the Earth's crust. It's like, it's everywhere. It's on every continent. It exists everywhere. And, in the form of, we have scrap on every covenant already. Yeah, so that's what it is. We think it's really big, Mark. We think it's really, really big.
That's super cool. Yeah. What's the cathode material?
Cathode, I can't get real specific with you what we're doing, but no rare earths in it. You predominantly, and this is well known, you use predominantly carbon in there, and then you'll have catalysts. It's the catalyst where you get the reaction to happen, a 3-part reaction that's going to take that oxygen, get it into solution in the forms of ions on the other side. So yeah, we don't disclose what we're using. That's part of our IP right now.
Keep the secret sauce secret. Yeah.
Yeah, we've got a couple of sauces that are secret. Yeah.
Yeah. That's good. I'll say it back. So this parasitic process, I guess, removes or corrodes the aluminum from the disc or plate and moves it to the cathode, releases electrons during the corrosion process. You've got a sodium hydroxide bath that you keep the whole system in, but then I guess air gapped on one side that's bringing oxygen into the system, introducing oxygen. Super cool.
Yeah.
Can you share, I guess, some preliminary numbers for like what a disc how much energy might be released? And you're holding this disc, which is awesome. I love props and toys and
yeah. So it's basically
an inch or a centimeter thick record player.
Yeah. So basically, the simple way, this is probably a kilogram. I'm sorry, on metric and in Canada, but so 1 kilogram, we're getting net in the first product out, we'll get 2 kilowatt hours of energy per 1 kilogram of aluminum. So this is basically 2 kilowatt hours of energy. And so when you look at that, how does that compare with gas or diesel? Pretty comparable, honestly, volume and mass. We're basically getting the same amount out that's usable. The advantage we have, that's just the electrical energy, so 2 kilowatt hours of electrical energy. If you can use the heat, there's some applications where you can use the heat. There's another 3 of kilowatt hours of heat. So, you start to think about cogen opportunities, Mark, long term. You come from petroleum industry, you understand all that stuff. So it's very, very comparable to a gas or a diesel, and that's just our first product. Our first demos are in that range. The theoretical max is to take that to 4 kilowatt hours per kilogram. I won't tell you how close we've gotten to that, but we've been pretty close. So you have a very viable, cost-effective energy carrier that I don't want to cast aspersions on hydrogen or anything else, but it's a good energy carrier. It's a really good
I like that you use the term energy carrier and not necessarily energy source, right? Like you still have to put energy into the aluminum the milling, the separation from ore, it goes and gets created into products, and then you're taking it after it's already been refined and might have some impurities. You use the word dirty. I like that, but it's essentially there's contaminants that are not aluminum in the material, and but that's okay for you guys. So, but it's not necessarily an raw energy, new energy source. You got to put energy into the aluminum first, and that's why the term battery or energy carrier is a better description, right?
Exactly. It is a battery, 100%. And just to kind of push a little bit on what you said, Mark, and this may be getting ahead of where you wanted to be, but
it's okay. Yeah.
Ultimately, ultimately, and this is a little bit to our vision, like we're starting with scrap aluminum as our fuel, and there's a lot of it. I can get into all that, but ultimately, what's possible is to take the off product. I haven't talked about that. You consume the aluminum, and then in your slurry is your aluminum trihydrate. Okay, that aluminum trihydrate we pull out in the form of a solid and can keep it in a slurry form. Today we sell that. It's a big market for that. We use it as a flocculant for wastewater treatment, so we can, every municipality buys ATH, and that's a great, source of cash for us actually, and the economics of the first product. But ultimately, you could take that ATH, okay, and you can make it back into aluminum. Okay, so the way.
I guess that was going to be one of my questions was, are there consumables in this process? If so, what gets consumed and how does that impact the economics? And I guess for listeners, I understand the word flocculant and I can guess at the chemical makeup of aluminum trihydrate, but those might be pretty technical for folks.
Yeah. You want me to go a little deeper on that?
Yeah.
I mean, sorry to use big words. I didn't know what flocculant was until they told me, because I'm not a chemist. But essentially, the off product is aluminum trihydrate, which is ALOH. And what a flocculant is doing in wastewater treatment is essentially it reacts and with the solids in the wastewater and makes them heavier, which allows them to settle. And there's a couple of different options, but aluminum trihydrate is actually the biggest one used in that wastewater treatment zone. So what's cool, like when you think about I get inspired by nature. I live in the woods, and what's cool about it is we're actually taking waste aluminum, okay? We're taking it back to its energy source. Then the off product, we're actually using to take human waste and kind of get it back to where it needs to be to clean water, right? So it's kind of, and to me, it's all been sitting there in front of our faces as humans for the last 100, 200 years, but we didn't really notice it. That this was possible. This was a way that things could be wired cost effectively, right? Which is, I think, the key. It has to be cost effective. But yeah, back to your idea about, and you said it well, Mark. Really, the way we start with scrap, lots of scrap around the world, and that'll be our focus for the first 10 years probably. But ultimately, our vision, and we've actually started another group called Gaia that I can talk to you about, is that we would have a fuel grade aluminum. So imagine the United States, now you have this aluminum trihydrate being collected, you have your own smelters in the United States that might be using whatever energy is the cheapest and available, creating a fuel grade aluminum. Now fuel grade aluminum, when we make aluminum today, for this aluminum on my iPhone, right, this is aluminum here.
For this tea can I'm drinking out of, right?
Exactly. This has to be, when you smelt this, 99.7% pure. Okay, those impurities are really, really important. I need 88% pure.
Yeah,
okay,
that's great.
Right, so now
that's a great threshold to have, right? Like that's way easier than 99.
It's way easier. It's way
easier.
It's
kind of like school, right? It's way easier to get an 88% on a test than
It is way easier to get an 88%. You can have a lot more fun getting an 88 than you can have getting a 99.7. I never saw a 99.7, so I can't comment. But so what, so we think, the way we're and we're not alone. We just started a group called the Global Aluminum Energy Alliance, Gaia. We're just going to launch in October in Boston. Started it with a company called Found Energy out of MIT in Boston. And they also can use scrap or dirty aluminum as a fuel. They take it to the heat. There's two reactions. You can either go towards electricity or you can go towards heat and hydrogen. And so we've come together and said, hey, let's consider this as an energy carrier. And we'll kick this thing off. And we think, fuel grade aluminum is a very viable energy carrier. Probably doesn't replace fossil fuels everywhere, but it certainly goes a long way to, our mission at AlumaPower is to vanquish the internal combustion engine. So we'll go a long way with fuel grade aluminum. On paper, it has to be proven out. On paper, we can get lower costs per kilowatt hour than gas and diesel. So
cool.
That's when you win the game.
So where are you guys at in the process, Rob? Like, do you have a prototype energy system, or what do you envision that these batteries? When people hear batteries, they think like AA, AAA car batteries. Not necessarily, maybe a Tesla Powerwall, maybe a bunch of cells pieced together, and then when I think internal combustion engine, I can see what a V8 and what a classic generator looks like with pistons and cylinders, but what do you envision the energy system looking like? And have you guys, start building anything? Or
Yeah, oh yeah. So last year, they said it publicly, so I'll say it publicly. A company called Purelator, which is a courier company primarily in Canada, launched our tech actually at a transit station, subway station in Toronto. And there what we were doing was they packages, last mile delivery with e-cargo bikes, very cost effective. But they didn't have they wanted to locate, they have a container right at the subway station or at the transit station, middle of a parking lot, no electricity. Didn't want to use a diesel generator, noisy, wasn't going to be right. So they were doing battery swapping, hauling lithium iron phosphate battery back and forth. And we came in and said, hey, we'll put our generator beside this. So we, it's big and ugly at that point, the state of the tech, but proved it out.
Big box,
that.
Right?
We got a big box, and we did it, and it went really, really well. And where we are right now is, I could show you going here because it's also mostly voice, but essentially we'll do 6 demos next year, 26, and picture just a 20-foot container that would have a bunch of our cells in it. And these cells, I showed you that disc, they're roughly this size, and these cells are turning inside the cells, or inside each one of these cells, and then there's lots of cells. There's 48 cells in a module that are producing the energy. And so that's where we are. It looks just like a 20-foot container with a bunch of things on the outside, but when you open up the modules, you would see these discs. And basically that disc that I showed you would run 20 hours at constant high power, and then you would exchange the disk and you'd be able to keep going. So if you need 100, our primary focus is actually backup power for critical infrastructure. So if you have an outage that's over 20 hours and you need to go 100 hours, like let's say, big weather event that's 3 days long, no problem. You can refuel as you go, and you can make sure you can handle that outage. And so that's what we're going to market with right now, and huge demand.
So how many kilowatt hours or megawatt hours fit in a shipping container?
Yeah, our first in a 20-footer, this is a kind of a half shipping container. The first one will have a peak power of about 100 kilowatts and 57 kilowatts of continuous. And then when we go to actual production launch, we'll be up at around 250 kilowatts of peak power and 135 of continuous. So you're now kind of right where the beginning of an internal combustion engine is in terms of power density, which is a really important thing.
Yeah, so like 100 to 250 kilowatts of power, but how much energy is stored?
Well, and the energy is like, again, you got to think about it like in terms of a fuel, okay? Unlimited, okay? Now, each one of these is 20 hours. So take your 135 continuous times 20 hours. That's how much you've got. I can't do that math in my head very fast, but what is that, 2.7 megawatts?
30 centimeter disc in your hand-ish, right?
And you've got you've got a lot of these in there. Yeah, you've got, I forget the numbers in my head, but at 57, you've got over 400 of these in the machine. Okay, so let's do the 57 kilowatts. 57 kilowatts, it's going to run 20 hours per disk, right? So what is that? About just over a megawatt hour per disk exchange.
Okay, that was the number I was looking for. Yeah, megawatt hour per disk exchange. And I guess once the disk is corroded and used or moved to your cation, do you have to move material out of the battery then, or out of the shipping?
So we have, if you can picture it, there's the 20-footer, and then attached to that is basically electrolyte management system. And I won't get into, there's 2 ways. There's a basic and an advanced system to do that. But essentially, if I think about the advanced, you then take that the aluminum trihydrate, you have to get it out of that solution. And once you get it out in the form of the slurry, the electrolyte can be reused, okay? Now you're consuming some water in this chemical reaction. Your water is becoming your H2O with your oxygen is becoming your AlOH3 if you do the kind of balance in the chemical equation. So, but your electrolyte doesn't get consumed. And so we have this other device, and depending on how big a footprint the customer wants to have, we can make it big and bulky and ugly, or we can make it smaller if they don't have a lot of space. And then what they do is you can size it for what you want. So let's say the customer, like I was talking to a customer in Australia last night, they were like, Rob, we want that system to go just the 20 hours. We only want to deal with a 20-hour outage. And so then, it's a smaller footprint. Essentially what you would do is whenever the disk exchange has to be done, there would be a fluid exchange. And that's where you would take the slurry, the aluminum trihydrate off, goes to the wastewater treatment, and you would add more water and get it ready for the next round. A little bit of the electrolyte as well gets lost in the AlOH3, and so that's how you do it. And so it's a little bit it's like a diesel generator, but instead of to think it through, diesel generator, you put the diesel in, right, and you get the energy out, and then we exhaust the off product to the atmosphere, right? For us, you put a solid aluminum in, and then the off product is this aluminum trihydrate. And if you do I could show you the graph, but essentially it's similar kind of mass balances, a little bit more for us in terms of the output, but it's in this slurry form that then can be used as a wastewater treatment.
Gotcha. So aluminum trihydrate is the product of the chemical reaction. And I assume there's just as much of that as aluminum you're putting in, or just, like you said, the material balance a little bit more. So, but that's benign.
Yeah, 2 times. Yeah, so it's actually 2 times. So for every ton of aluminum, you get 2 tons of aluminum trihydrate. And the reason is because you've absorbed those OHs from the water and the oxygen.
Right. But I assume that's benign and can just be disposed of in landfill, or?
No, so that's got value. So that aluminum trihydrate sells for about $400 a ton, and so significant part of how this
for
the
wastewater treatment. You're saying
exactly.
We're not only generating electricity, we're also generating a commodity that can be used for wastewater treatment. Exactly. I was just thinking, if you generate too much, if your aluminum batteries really take off, and you're generating a lot of aluminum trihydrate, you could flood that market, but that'd be a great problem to have then, right?
Yeah, it's about an $8 billion market. I think we'll be okay for the first 10 years or so. But we use a lot of ATH, and then remember the ATH ultimately is if you can get it to smelter grade, you're making aluminum again, and that's an even bigger industry, right? It's also used for fire retardants in wires. It's used to make ceramics. It's used. You can make eco cements out of it, so cementitious material. It's got a lot of uses.
I love the approach of byproducts are valuable. I mean, this is like the carbon capture sequestration industry that is using CO2 to steam flood or to flood and have enhanced CO2 recovery for oil fields. It's like our waste is actually a product. So,
No,
how much water do you have to input then?
I should know that off the top of my head, Mark, but I don't. I apologize. I should have that in my head.
It's okay.
But it's not a huge amount of water. I mean, like if you do the chemical balance, it's not a huge amount. For example, we have a customer a big part of our focus and where the demand's coming from right now is in data centers, and specifically backup power for these AI data centers. And so as we've been kind of engineering this system for them, their condensate from their cooling process, the water they're sucking out of the air is enough to run our power system that keeps the whole data center going. So it's not a lot,
Gotcha.
but it's significant. I mean, these data centers are huge, so it's still a lot of water, but they're doing a lot of condensation.
What a great synergy, right?
Yeah, and we're not alone. Like the way you're thinking about this whole system, honestly, when I've been talking to a bunch of the hyperscalers, and that's the way they think too, right? You have to when you're talking to this scale. You have to think about every one of the products. Make use of it.
Did I hear this correctly then? A megawatt hour per shipping container per fuel load? I used air quotes there.
Yeah, if I did my math right in my head, which is dangerous, but yeah, about megawatt per disk exchange. Yeah, for the first one, and the next one will be much higher than that. It will be closer to a couple of megawatt hours of energy per 20-foot.
Okay. So if you had a 10 megawatt hour or 10 megawatt data center, you could have 10 of these containers on site.
Yeah. So what? Yeah. Let me think. You got to think about power versus versus duration, right? So think about the rated power. So if you had a 10 megawatt, and I'll go with the actual production version, you're getting 100, and you needed 10 megawatt continuous, Mark. Okay. So 10 megawatts, we'll be putting out 135 kilowatts, or whatever, 10 megawatts divided by 135 will tell you the number of 20-foot containers we would do. But what's nice about this is because we don't have any of the thermal runaway issues of lithium, and these can be stacked. Okay, it's a very modular system,
vertical,
right?
yeah.
We can go vertical, right? And that's, I mean, I don't want to go too far into what we're thinking about there and what we're doing. We haven't got all that.
So how do you reload disks on the fourth layer up? Like,
yeah, it's start thinking about automated warehousing, and you'll start to think about where it's all going. That technology is available to do disk exchange, and so that's really where we're going. Is this can all be automated? Now you've got Now you've got a very high power backup power system with zero emissions.
yeah.
And it's dispatchable. It could be, you can turn it on whenever you need it, which I think, in grids right now, that's a huge issue as we adopt things like solar and wind, which are very, very cost effective, but we need dispatchable power when we need it. And we need it, I always think about it like a tree. We need it at the leaves of the tree where the solar is. We don't need it at the trunk, right?
Yep.
Because if we put it at the trunk, we have to rebuild our whole network. So that's kind of where we're going.
How, I guess, is the 20-foot shipping container kind of like the optimal size, or would you envision making these smaller or even more energy dense?
Yeah, the way
we're thinking diesel about generator sometimes, and I guess that doesn't necessarily mean a diesel engine in a vehicle, or maybe it does. Like, would this be in a vehicle eventually, or?
I believe it will be, actually, but let me talk about a little bit. Like it's technology adoption. So we've chosen stationary power as the first stop, partially, honestly, because it's easier.
It's easier. Yeah,
it's easier, and there's a huge need. Right? There's a huge need right now with these AI data centers and backup in particular. But the whole thing, it's actually an immersed, it's the fluid is encapsulated, and so it absolutely it can go mobile, absolutely can. And so the thinking is we get up to the millions of cells with this application, get down the cost curve, so we get the actual machine, what we call the galvanic generator, is primarily an injection molded plastics machine. Okay, it's not high heats in this thing, so we don't have to spend the same amount of money that internal combustion engine to make metals, because we can do this out of plastics, which is really nice because it helps your costs. Like, I'm an ex-automotive guy, injection molding is a fantastic process, and it can be very cost effective. It scales really, really well. So once we get the cell cost down, which won't be difficult over this next 3 years, now you can use those cells wherever, right? And as long as you have the power density, now you can go into mobile applications. So yeah, that is what ultimately will happen, is these will be adopted. If you take that automotive example that you were just saying, we see ourselves as the energy density solution. We think rechargeables like lithium ion phosphate are the power density piece of the equation. So lithium ion, fantastic for dumping electrons quickly, right? It can deal with all your transients, but kind of sucks when it comes to range. And we'll get better on range, but when you think about it from a cost for range, it's pretty darn expensive, right? Cost per range, cost per kilowatt's all right, but kilowatt hours, it's not so good. We're the opposite. We've got you range. Our cost per kilowatt hour is infinitesimal because of the refueling, right? So if you put these two together, now you can make the rechargeable system smaller, lighter, right? And we provide the longevity and the fuel. So we call it the all-electric hybrid.
You heard it here first. Fire Division podcast. The two hybrid systems, two battery, different types of battery hybrid vehicle.
Yeah, all electric
I've never
hybrid.
considered that, Rob. That's really cool. Yeah,
It's the all electric hybrid.
I'm sure you've told
And,
other people. I heard it here first on the podcast.
Okay, yeah. Well, it's
Crazy,
not the
yeah,
first time.
yeah.
Yeah, and what like just to kind of add on to that, where it really starts to sing, is is in marine. So in marine, remember, well, not remember, a huge part of our weight and system is actually the weight of that electrolyte because it's water, right? It's an aqueous solution.
Yeah.
But marine, wonderful. You actually have you're sitting on a bunch of salt or fresh water. Both work for us.
I was going to ask.
So
yeah,
now
saltwater still works. So you've got your
works
electrolyte
really well.
built in if your electrolyte's salt. But
Yeah, you're right, Mark. So now I'm leaving the dock or I'm leaving the pier. I don't have any of that electrolyte weight. We've already created a unit that makes the electrolyte on board from a solid, and so now you've got something that's don't quote me. I'm going to guess it's going to be about 5 times the energy density of lithium ion. So now we actually have a new power source for marine that works. Right now, lithium ion batteries, it's tough to get. I'm a water skier. I'd love to buy an electric boat, but it's not. It's with lithium ion, it's just not going to happen. That I get my electric boat anytime soon.
yeah, but you think with this hybrid system you could.
That's my dream. I want to be pulled. I want to be pulled before I go to my grave by
With
one of these
knowing
all
both,
electric hybrids.
right? It's mostly for the health of water skiers. We need to have hybrid boats. That's awesome, Rob. So, well, we talked a lot about the tech because it's interesting and it's different and very, very different, innovative. What's the business look like now? You mentioned that you're mad scientist that came up with this, tech guy, co-founder, and yourself. You've been with the company since 2020. How big's the team? You've done one prototype. What's the go-to-market strategy? Where are you guys at in that process? Fundraising? Talk to us about the business.
Yeah. So team roughly 50 people at this point. Fundraising, just finishing off a Series A fundraiser. We have raised on that round probably just over 14 million US. Lots of government funding. We're going to launch 6 demos next year in 26. We've probably sold 3 of them so far. So we're just talking to other customers about those demos. And they will be primarily focused on backup power for critical infrastructure, data centers and utilities. One of the customers is going to use it for a EV charging, a flexible EV charging system, which is fine. That works. And that's where we are. And so we've got, we're really just focused on, we just did our Alpha 1 release, which is the first design freeze 2 weeks ago.
Alpha
And
1, is that a product name or?
yeah, it's a prototype name. Like it's so I'm out of automotive. We use what's called the APQP process, Advanced Product Quality Planning process, and that's your first build of something that's production intent. And so those will be available, and then we just go through cycles, through hopefully total of 4 cycles to get to the actual big product launch using an injection molded tools as well. So we're really, we've been part of a number of different accelerators around them, and one of them was called Free Electrons. Free Electrons was or is 7 different utilities from around the world that we're trying to figure out how to adopt new tech quickly, and they created this accelerator where they go through a rating process. We were selected out of 800 into the top 30 globally, and out of that has coming some POs now, purchase orders, to do some demonstrations for these demonstrate the technology, and then the idea is that we demonstrate with 1 or 2 of those utilities and then those utilities can then adopt it in their local markets. So we're in negotiations right now with a few of them to do those first demos. So that'll be for how the utilities adopt it. But the other really big demand is from the data center side. Hyperscalers are all coming to kick the tires in September. The hyperscalers, I'm sure you talked about it on your show, the demand for these AI data centers is just huge. But how do you build out power? And the fastest way to power is solar and wind. The turbines, there's not enough turbines. We're already 5 years lead time now on natural gas turbines. So the fastest by far now is solar and wind. But the solar and wind comes with this huge issue around what happens for when you're out of either sun or wind for 3 days. Okay? Go-to would be a diesel generator. Diesel generators, you won't get air permitting for beyond about 24 hours in all the states, United States. Okay, so it doesn't work, and that's where we come in. So that's really what they're looking at it. That's for right now, and that'll be honestly, like, if those hit, even some portion of those hit, we're busy as heck for the next 5 years, just building a lot of these systems.
So it sounds like, Alpha 1 frozen design ready for production. What's your timeline to deployment? You said purchase orders, like you're going to do some prototype test sites or...
pilots or demos.
Pilots
those will be Q3 and Q4 of 26. We'll do a bunch of these demos. We'll get the feedback. There'll be problems with them. We'll work with these customers, and then whoever those customers are that kind of take a risk with us and work with us on those demos, they get first dibs on the production version, which will launch in the second half of 27, and that's where we'll ramp up. And in 27, 28, go to build out. There'll probably be one more design iteration, I'd guess, in there by 28, and it's pretty big. It goes pretty big, pretty fast. Assuming that some of these things, because they're talking big numbers, they want a lot of power. So at the same time, we've had to
10 megawatts, and that was like the smallest data center that
exactly they want.
I think Comcast has a 6 megawatt data center outside of Denver that is like cute, right? Like these other ones.
They are cute. Yeah, like really, what they really want is a module would be about 2.7 megawatts. That's kind of the first piece, and that's where we're aiming. We are aiming to go to gigawatt scale. And so we're developing the ability to make the galvanic generator at that scale. As I said, it's injection molded. You can see your way through to making that. A lot of those things exist. The other piece of the equation is we've got to get the fuel supply, right? So I can't say publicly.
We actually need some aluminum.
We need aluminum. But we just did a JDA with, I can't say their name because I'm under NDA, but one of the biggest in the world. And the good news is there's a lot of scrap in the United States. And so we're with one of the largest scrap collectors. That's joint venture with this other company. And so to kind of put this thought in your mind, we're talking in the United States about energy security and everything else. Kind of quick numbers. Today, the United States is selling a huge amount of scrap to China, okay? And so if we diverted a quarter of that scrap and instead used it for backup power in the United States, that would be enough to power 10 of these gigawatt size facilities in the United States. And so that's our vision. Instead of sending this offshore, we want energy security in the United States. It exists here already. It's all these primarily scrapped automotive vehicles that have been chewed up and mixed metals. We can now use that as our backup power, married together with solar or wind, or it could be natural gas, or it could be small nukes. It could be a bunch of different things that we're agnostic to the energy source, whatever's cost effective.
Yeah, the story sounds good with solar and wind, but applicable to everything, right?
Yeah, it is applicable to everything. Like a lot of times, one of the things people really like, and it's another kind of thing I never thought about, but what's cool about our tech is it's cellular. So, if you think about a natural gas turbine, they're big, they're wonderful, but if it goes down, you're out for like 4 months, right? So, whereas with ours, because it's cellular, like at a gigawatt, we'll have millions of these cells. Well, what if like 5% of them don't work? No big deal.
Yeah.
Right? You can still provide the power. We probably size it at 1.25 or something. So it's a little bit like the way they work these data centers. They have redundancies and they have extras and they work around all the problems automatically. That's the kind of energy source we have here. And unlike lithium-ion batteries, they can do some of that as well, right? So it makes for a more resilient energy base in many ways.
Yeah. Rob, what's the world look like in 5, 10, 15 years for you guys? I mean, you've got millions of these things built and you're starting to recycle them. I mean, yeah, give me the vision.
I mean, as I started kind of with our ultimate mission is to vanquish the internal combustion engine. Okay, so, and it takes a while to vanquish something that's been around for 140 years. But 10, 15 years, what I would hope to see is, in terms of the backup power and critical infrastructure and the use of scrap, that is well developed and going well. I would really love to see a fuel grade aluminum being smelted in the United States and Canada and around the world, and that's beginning to take off as a very formidable energy carrier globally with us and with other technologies that can use a fuel grade aluminum. And but I think it's a very diverse energy landscape. I don't think there's one size fits all, one tech that fits all. I think we have wonderful technologies. Like Jeff took really old technology and put it together with new technologies. And the good news is we keep inventing new technologies. So I think as humans, what we have to do is we have to realize, and we have all these wonderful tools, how do we put these things all together to get a very low impact energy system, but one that's cost effective, that one that can be shared around the world. And energy, you focused on it in your show, Mark, which is great. Like, there's such a huge correlation between energy usage and costs and economic growth and health, right? Like, the two go together, right? There's a perfect correlation. So to me, I've made lots of money in business. It's a little bit the reason why I'm here. And after dangling on that rope that I talked about at the very beginning, like, what are you going to do with your life? This is about, let's leave it a little bit better and try and leave it a little bit better and take some of these capabilities that we have with AI now and think it all the way through. Think away all the circles, like you talked about, thinking about the waste product. And honestly, one of my inspirations, like I'm a Christian guy, and I think a lot of this is faith-based for me, but it's also just look at nature, how nature works. Nature never has a byproduct they don't use again, ever. Right? I live in a forest. Every tree falls down, turns into dirt, makes another tree. That's the way we have to think in that whole cycle. So that's the world. And I think as humans, it's hard. We can get pessimistic when you look at the news and wars and all these other different things. But to me, I'm very positive. We have the abilities to build something that's good for the world and good for those in need as well. So that's my vision.
Awesome. I love it. That's a great place to leave it. So, Rob Alexander, thanks so much for chatting with me. Excited for you guys. Excited to see where you go.
Thanks a lot for the opportunity, Mark. Appreciate it.